thank you very much, Miles, Monica, and Angela for putting this together. It's a very nice program. So today I'm going to talk about singularities in the Euler equation. And the talk is not going to be very technical. So I'm going to be presenting sort of some ideas and broad lines. Yeah, I hope most people should be able to follow. Okay, so let's start. So first, let me just recall the Euler equation. So the Euler equation is a PDE which models the evolution of a velocity field. So you have U is the velocity field of an ideal fluid, and omega is the domain of the fluid. Okay, so mostly we'll be thinking about omega as the whole space, and R, and it also depends on time, and it outputs a vector, so the velocity. Okay, and we assume that the velocity is incompressible, which means that the divergence of the velocity is zero. So it's not possible for many particles to be squeezed in a small area. And the equation goes like this. So the pressure P, the purpose of it is to keep this divergence-free condition. Okay, so you supply it with an initial value, and okay, if you're on a domain, a bounded domain, you give it a boundary value. So you don't prescribe the velocity on the boundary, you just prescribe that it be tangent to the boundary, so that the particles cannot escape the domain. Okay, so this is a very old system. Was derived in the 1700s, and okay, it seems to be the second PDE ever written. Though okay, much is still unknown, and many difficulties associated to analyzing this equation. It's a system, so it's not a scalar equation, it's non-local. Okay, so in order to keep this divergence of U is zero condition, you added this pressure, right? But then this is a non-local equation, right? So if you take the divergence of the equation and solve for the pressure, you have to solve, P can be found by inverting the Laplacian, which is a non-local operation, right? So every part in the fluid kind of immediately feels any disturbance far away. The third thing is because it's an ideal fluid, and because in reality, if it's modeling what it's supposed to, then you should see many very small structures forming. So they shouldn't be able to control the solution very well. And furthermore, an interesting dynamical fact is that there are many stationary states, and to my knowledge, we still don't have a very good understanding of the global picture of the set of stationary states. Okay, so there are two sort of important directions that one can classify work in the Euler equation sort of in two categories, I think. So the first one is to try to understand the well-posedness theory of the equation. So to try to get a notion of solution that is good for the equation. Okay, so okay, it's like you could either think that you want to study weak solutions or strong solutions, or okay, with the problem with weak solutions is the uniqueness problem. The strong problem with strong solutions is the problem of singularities. And okay, you could also look at sort of Taylor made notion of solution if you're thinking about specific kind of problems like water waves or similar. The second sort of step, so once you have a good notion of solution, is to look at general qualitative behavior. Okay, so examples of this would be talking about stationary states and the local behavior around stationary states. Is this about stability and asymptotic stability and things like that? And then, okay, you can start to look for more exotic things, and you can also ask about generic behavior. So in this talk, I'm going to try to discuss mechanisms for breakdown of classical solutions. And okay, one can sort of put this, so that for the finite time singularity question, I'd say it's more sort of in the first category, but these two directions are sort of intimately related, so it's kind of difficult to separate them. Okay, so let's start with the two-dimensional case. So I want to talk a little bit about infinite time growth for solutions to the 2D Euler equation first. So it turns out many of the ideas here are, so this is what I would call the breakdown problem for the 2D Euler equation. So the problem of breakdown of solutions as time goes to infinity. Okay, so we're going to discuss the available conservation laws. We're going to discuss instantaneous mechanisms for growth. And then we're going to discuss a little bit how you maintain these mechanisms for growth. Okay, so in 2 dimensions, it's useful to introduce the vorticity. So it's a scalar. So omega is this. So this is the same as if you viewed the fluid in 3 dimensions, but only depending on as the velocity in 3 dimensions, only depending on 2 variables and only having the first 2 components, and then you take the curl. So the 3-dimensional curl, you get a vector with 2 zeros, and the final component is this thing. So this is the vorticity. So it's the natural 2-dimensional version of the curl. Okay, since the divergence of u is 0, you can recover u from omega by this Biot-Savart law. And it's not difficult to check that omega should satisfy this nice transport equation. Okay, so in 2 dimensions, what's happening is that the vorticity is being transported by the velocity, and then the velocity is being determined by the transported quantity by this law 1. Okay, so it's called the Biot-Savart law. Okay, so let's now talk about conservation laws. So since it's a transport equation, okay, it's clear that you have a pointwise conservation of the L infinity norm. But since the divergence is also 0, you can show that in fact, there are infinitely many conserved quantities. So any, if you have X is any rearrangement in variance space, so like LP or similar, then the X norm of omega has to be conserved for all time, okay, as long as omega is a sufficiently nice solution. Okay, so stronger bounds do not hold in general, so it's a nice exercise to check that if X is any space compactly embedded in L2, then you cannot prove any global a priori bound. So in the sense that you could construct a solution which starts very small in X and after later time becomes arbitrarily large. Okay, in fact, one can even conjecture that in any regularity space, the set of initial data for which the solution is unbounded is open and dense. Okay, so this is just a conjecture at this point, and it's I think, a very interesting problem to study. But okay, the point is that essentially you have some bounds, but then after that, other than sort of the obvious bounds, you should not have anything else, anything stronger at least. Okay, so now, okay, in this, I want to give you an idea of how, solutions could possibly grow. So growth, as we said, is not, you cannot have pointwise growth of the vorticity in 2 dimensions. So growth can occur at the level of the derivative. So sorry, so a lot of things just appeared now. So you define capital omega to be this quantity. So this perpendicular here is for convenience, to make the equation look nice. So this, you could have looked at the normal gradient, but anyway. So capital omega satisfies this, is transported and is being forced by this quantity, right? So if you want to talk about the pointwise growth of omega, or even, LP growth of omega, capital omega, then you have to think about this term on the right-hand side. So gradient of u times omega. So since u is divergence free, this matrix gradient u is trace free. And since it's trace free, it means its eigenvalues have to add to 0, right? So at any point, the gradient of u can essentially take 3 forms. So first case is sort of a rotation, pure rotation. So that means the eigenvalues are pure imaginary. Or it can be a shear, so that means a double 0 eigenvalue. Or you can have a hyperbolic structure, okay, where you have a positive eigenvalue and a negative eigenvalue. Okay, and the sum has to be 0. Yeah, so essentially locally, if you're talking about growth, you can check in these 3 cases what happens. Okay, so if you think, I mean, it's just caricaturing the situation a little bit. So it's easy to see that if locally the gradient of u is just a rotation, of u is just a rotation, there should be no growth of omega. And in the case where, in the second case, in the shear case, you can get linear growth, so algebraic growth of high derivatives. And in the hyperbolic case, you should be able to get exponential growth. Okay, so this is just, caricaturing again. Of course, if normally you don't have just this behavior, there could be like a constant in the front. So if it's possible to amplify gradient of u also, then you might be able to get faster growth. The rationale for there being generic growth in the Euler equation, if I can just mention it for 1 second, is that generically you're not going to have just the first case. Generically, you should have some points in the fluid where there's either shearing happening or hyperbolic structure. And generically, further, at those points, there should be non-constant vorticity, right? And so there should be, in a generic fluid, there should be vorticity growth, or not vorticity, the capital omega should grow. So the derivative of vorticity should be growing. Okay, of course, establishing this rigorously is a different story. Okay, so to make, this is sort of instantaneous growth. So you could, if you had initial data, say, which had a certain structure, you could certainly ensure that the derivative of omega grows a little bit. So that's pretty easy to do. But then how can you sustain this growth for all time? Okay, so that's the next thing. Okay, so regarding this generic thing, I forgot to say, so there's a paper of Koch from 2002, which you can look at if you're interested. Okay, so how can you sustain growth? Okay, so I'm just going to look at the hyperbolic case. The shear case, how you sustain sort of a shear structure, is a slightly different issue. But okay, in one word, you can try to use like some low stability at sort of low regularity. So if someone's interested, you can ask me later. Okay, so if you want to, so again, the velocity field is determined by the vorticity, and then the vorticity is transported by the velocity. So question one can ask is, how does omega have to look to ensure that U has a hyperbolic point? Okay, so this is kind of a general question. So, I mean, really what's behind it is, what information, which is also propagated by the Euler equation, can you impose to ensure that U has a hyperbolic point? And okay, one way to think about it is that the hyperbolic point of U is just a saddle point of the inverse Laplacian. Okay, so remark, it doesn't make sense to think about very quantitative conditions. Okay, because at the end you're trying to prove some instability or growth. So it's better to think about conditions which are like symmetries or positivity or something like that, right? Something which doesn't have any quantitative nature. One way that people have discovered is to impose some symmetries on the solution. Okay, so in particular, if you assume that the vorticity is odd with respect to two or more lines, then the velocity, generically has to be hyperbolic at zero. Right? So you can think about this as, this saddle point issue. So if you have, say, many maxima and minima, which is what's forced by having this odd symmetry, then you have to have a sort of a saddle point in the middle somewhere. Okay, and this odd symmetry, one good thing about it is that it's propagated by the nonlinear dynamics. Okay, so a quantitative version of this idea is the key lemma of Kiselev and Shverak, but I've also seen it before in work of Iftimi and collaborators from '99, and probably it even precedes that. And I'm going to discuss this issue a little more later. So let me discuss the analogous issues in 3D. So in 3D, you get, I'm using the same variable capital omega as I use for the vorticity now. So this is really the curl of the velocity rather than the gradient perp of the vorticity. And it satisfies, again, this type of equation. So now everything that was true about the gradient of vorticity in 2D basically becomes true about the vorticity itself in 3D, right? And this is the main difference. So the vorticity equation is not just conservative now in 3D. Okay, so capital omega itself can grow, and if capital omega itself is growing, it's the gradient. Capital omega is just the curl of U, so the gradient of U is also growing. And if you align, if the growth is aligned in the right way, then the equation will become reminiscent of a Riccati type equation. Okay, so this I put in quotation marks because omega is a vector, so this is not really correct to write this, but something like this can be established in some scenarios. So I'll talk about that near the end. So as is done in the problem of long-time growth for 2D Euler equation, so our goal is to isolate some kind of instantaneous growth mechanism, which again will sort of be hyperbolic points. And then you try to impose restrictions on the solution to sustain the growth, right? So like in 2D, we mentioned this thing about symmetries, and the symmetries will give you that there's always a hyperbolic point at the origin. So now you want to think of slightly more sophisticated versions in 3D of that idea. Okay, so now I'll jump to the 3D case. So I want to talk now about this sort of two specific strategies for finite time breakdown in 3D. So the first strategy is reduction of the equation using the symmetry properties of the equation. And the general idea is that okay, the more symmetries you impose on the equation, whatever they are, the simpler the system should behave, right? So if you impose too much, of course, you might end up, having no motion, right? So you may end up essentially in a stationary state. So one has to be careful as to what exactly you do. Okay, so if you just think about the equation a little bit, so capital omega now, the domain I'll think of it as being just the whole space. So we don't have to worry about the domain and symmetries. Okay, so just think of the whole space. So okay, so clearly that you have translation invariance, you have rotation invariance. So because there's no preferred position or direction, or there's also scaling invariance in space. So you have this, if you have a constant lambda, which is non-zero, and you have a solution, then you can get another solution by scaling it in this way. And okay, same for rotations. And you also have a time scaling, which you can use. Okay. And all these symmetries can be used together or individually to reduce the complexity of solutions. So for example, using the translation invariance, you can sort of pass from the 3D Euler equation to the 2D Euler equation, and then from 2D Euler to sort of 1D Euler, which is a class of shear flows. So that's when you go that far, you've sort of gone to stationary states. And then you could use the rotation symmetry to get sort of radial or axisymmetric solutions. You can use the scaling invariance to get scale invariant solutions. And a combination of the last two will give you self-similar solutions. Okay, so the main thing which, so most of these things are very classic. So obviously these scalings have been known for a very, very long time. And these specific things like axisymmetry and passing from 3D Euler to 2D Euler and even self-similar solutions have been known for quite some time. So with Inji Jiang, we essentially found a way to describe scale invariant solutions. Okay, so let me talk about that a little bit. So what does it mean, scale invariant solution? So you want a solution which is invariant under the scaling. So no matter what lambda you put, you get the same thing out, right? So you can try to consider data of this form. So it's basically one homogeneous velocity. And such data, we're calling it scale invariant. Okay, so formally, if you have an existence and uniqueness theory, then the scale invariance will be propagated for all time, right? So there are some issues with this. First of all, the data would only be Lipschitz continuous unless you have just a linear function, which is not very interesting to study. The second issue is that you have linear growth at infinity of the velocity field, and even if you have smooth data, if you have linear growth at infinity, there's no general existence and uniqueness theory to cover all such data, as far as I know. And furthermore, okay, so the Euler equation has natural energy conservation in all dimensions. So even if you did understand these kind of solutions and you could give them meaning, it's not clear that they would say anything about finite energy solutions. Okay, so despite this, we were able to use this. So I'm not going to go into great details on this issue, so I just am pointing it out as an interesting direction of study. That's still, I think, there's still many open questions that one could consider. So, so using the scale invariance idea, with Ng-Jiang, we could establish the following type of general theorem. So you can build an existence and uniqueness class for the n-dimensional Euler equation. So we worked in 2 and 3 dimensions mostly. So there's an existence and uniqueness class, which embeds in the space of Lipschitz continuous functions, so that you can solve the Euler equation locally in time, in 3D, but you can get singularity in finite time. Okay, so this is the type of growth I was discussing earlier. Okay, so so we considered basically 2 cases. So one case is this like hourglass-shaped domain. So it really has a corner in the domain. So it's yeah, if you think about it a little bit, you realize that it's like a cylinder, but it has a little kink in the middle. So you can consider such a domain, or even the whole space. So there's a bit of technical work to deal with this issue of the regularity issue, but the main point becomes that you want to prove finite time singularity for the class of scale invariant solutions. So scale invariant solutions, remember that they are, if I can go back, remember they're satisfying this condition. So essentially, by imposing this condition, you reduce the degrees of freedom in the equation by 1, right? So if you add another symmetry, like some kind of rotational symmetry or axisymmetry, you can reduce the degrees of freedom another time. So it's an idea we did in the first result in this direction. If you do that, you just get a one-dimensional system of equations. So, okay, so let me just remark, you know, that basically you you just plug in the ansatz that the velocity is one homogeneous and maybe with some rotational symmetry, and you can easily derive this kind of equations. Okay, so it's not precisely this, but yeah. And the idea for studying this kind of equation, so you have this quantity little g and capital P, okay, and you observe, and little g is being transported by something, by capital G, and capital G is determined by an elliptic equation. So this is kind of like a one-dimensional version of an Euler type equation, right? So, the question is, how can you ensure that little g and capital P are sort of growing, right? So little g is being forced by capital P, and capital P is being forced by this quadratic nonlinearity, which is determined by little g. And you sort of have to build a situation where you have growth. So for example, and again, you know, to establish the growth, you're not really allowed to say that, you know, little g remains close to something or capital P remains close to something. So you have to think sort of more broad terms. So one example of something you can say is that if capital P, you know, starts out as a positive function or non-negative, then it remains so for all time, so long as the solution exists. So this is just like a small ODE argument. And okay, that's good. So that means that, you know, G is being forced by something which has a sign. So let's try to give G the same sign so that there's some kind of growth. And then you try to make the same sort of arguments on derivatives. So in one dimension, it's one of the advantages of one dimension is that you can make these kind of statements about positivity. So it turns out that for this model, you can propagate a number of positive quantities. So you can prove that if it's initially so that P and its derivative in theta and G, and even about second derivatives of P and the first derivative of G, all of these can be made positive, right? So, so that then you can expect that there's some kind of mechanism which you can use to get growth. On the technical side, what this amounts to, so passing from this sort of formal calculations, so I would say that before you have an existence and uniqueness theory, you know, talking about scale invariant solutions is just a formal thing, right? So how you actually prove that they have relevance, say, to finite energy solutions is using some, I think, deep study of elliptic problems in corner domains, okay, or elliptic problems that, you know, around L infinity actually. So, okay. Okay, so that was one, you know, I think fruitful strategy to attack the global regularity problem. So next, I want to talk about another strategy, which is basically how you pass from approximate equations to the full equation. So you can imagine that, okay, say you want to prove a blow up for a certain equation, and you know you have, and say in certain scenarios that it looks kind of, it's a perturbation of another equation where you know that there's blow up. Okay, so how can you pass from approximate equation to the full equation? So this is sort of different from what I said before. So I said before that, you know, generally you cannot do any quantitative statements about, you cannot impose quantitative conditions on the velocity. So I said you should take symmetries and positivity, maybe things like that. So in this one, you're now going to try to think more quantitatively about true stability statements. Okay, so let me try to give an idea of what I mean. Okay, so So I'm passing now to the old notation, which is little omega. So sorry about that for the vorticity. Okay, so there are two things which are happening to omega in 3 dimensions. So it's being transported by this first term, and it's being stretched by this term. Look on the right-hand side. And the growth is really coming from the stretching term. Okay, so to understand these two terms, we have to invest lots of effort to understanding this mapping, omega to grad u. So this is what I was saying about, what can you impose on omega to make sure that u has a hyperbolic point? Okay, so what can you impose on omega to, so if you know something about omega, how can you say something about grad u, right? So this is, in 3 dimensions, it's written this way, that grad u is just the gradient of the curl of the Laplace inverse of omega. So this is because u is divergence free. So the curl of a divergence free vector is just its Laplacian. Okay, so it's easy to see that you can recover u from omega in this way. Okay, so it's well known that this is a singular integral operator, and that this type of operator will be bounded on LP space and on CK alpha spaces when alpha is strictly between 0 and 1. And in particular, it's not bounded at the boundaries, so on L infinity and on C0 or C1. And this is because the kernel of this integral operator is non-integrable, both locally and at infinity. And the two are kind of dual to each other. So the first thing we'll try to do to understand this problem is to see what happens when alpha goes to 0. So you have bounds on this operator in C alpha for alpha positive, and we want to see if we can describe the degeneration as alpha goes to 0. Okay, so alpha going to 0. Okay, one way to think about it is that you're talking about general C alpha function. Okay, maybe that's too broad. So you think about smooth functions of this variable, x to the alpha and the angle. Okay, so this what I call a nice C alpha function. Right, so C alpha function can be really crazy, right? Because of this, can have this Weierstrass type functions and things like that. So that's too crazy for us. So we think about this sort of nice C alpha function. Okay, so you think K is minus D homogeneous and mean 0 on spheres. So K is some kernel. And you consider this operator, which is understood in the principal value sense, this integral. So this is, of course, the Biot-Savart law. So the law which gives gradient u from omega is within this class. Right? So you can think of it as a minus D homogeneous operator, integral operator. Okay, so you try to think about it. So you plug in a function of x to the alpha to this. So okay, so you write in polar coordinates first, and now you want to see what happens. So let's make a change of variables. So we call capital R to be y to the alpha, right? And then you get this nice, just a change of variables. You get this 1 over alpha in the front, and for when the derivative hits the inverse of this mapping. And okay, you have these elements here. And then, okay, now you use that K is minus D homogeneous, and you can pull out of it this r to the minus d over alpha, right? And that cancels directly with one of the terms from the volume element, right? And you just get this, right? So this is the form of, if you're given a capital F, then this is what capital R of F is, right? So now when you send alpha to 0, you see that you have this 1 over alpha in the front. Okay, so it makes sense then to multiply by alpha and then send alpha to 0. And if you do that, then what happens is that this k, let's see. So when capital R is small, right, smaller than something to do with capital X, with the modulus of x, then this has to go to 0, right? Otherwise, it converges just to that, right? So then the inside, the argument, so either the argument here goes to infinity, or this thing goes to 0, right? So if it goes to 0, you get this. If it goes to infinity, k is negative homogeneous, so this will go to 0, right? So you just have this very nice formula, okay, which I think that, I mean, out of everything discussed, this is maybe one of the newer things, right? That if you think about the Schauder estimates or you know, singular integral estimates in C alpha, and you send alpha to 0, there's a clean way to figure out what you get, at least when the kernel is minus d homogeneous. If it's not homogeneous, then maybe you have to think about it a little bit. But in any case, you get this kind of formula. Okay, so this is kind of a formal pointwise computation. And from it, you see that when alpha is very small, you can write R of F as being this. So you have a leading order term of order 1 over alpha. And then, okay, in fact, you have a little o of 1 over alpha here. That's kind of what this computation gives you. But in general, you can actually show it's big O of 1. Okay, so the remainder is really a bounded operator. And okay, one of the main results of recent work we did was to justify this expansion in L2 spaces. Okay, so first you find this, okay, and then you want to justify that the expansion, this limit actually holds in an L2 sense. Okay, this hasn't been done in general, but okay, so for the second derivatives of the Laplacian, which is a particular case of this, it has been done. So a consequence of this computation is that you can imagine, okay, so maybe I take 5 more minutes, sorry. I'm going kind of slow. You can imagine whenever, if you have an equation, like Euler equation, you can imagine replacing this sort of singular integral, more complicated thing, just by the leading order term, okay? As long as we're okay with studying this type of functions. And the above is motivated by something I mentioned earlier, this key lemma. Okay, so in particular, if you make this change of variables, x to the alpha in the Euler equation, in particular in the Biot-Savart law, you can rewrite the Euler equation as a singular part. So you have these first 3 terms, and in order alpha nonlinearity. So this is like the other terms, okay, where gradient us, the singular part, is what's determined by r bar. So the r bar is this operator I mentioned over here. Okay, so one nice thing is that the gradient of US is a radial function, and US has a very simple dependence on x over x. Okay, so one can start with the alpha equals 0 equation, if that makes any sense. And you get this nice closed system, which has not been investigated in general. Okay, so this, I think, a lot of interesting dynamics that can come from studying this equation. And the simplest case, which is something we recently studied, is the case where you look at this equation in axisymmetry without swirl. Okay, so I'm kind of telling the story in the opposite direction, but it's okay. Okay, and the main technical part of this work is to introduce non-smoothness in angular variables. So let me just stop here for a moment. So basically, the way you think about it is that if omega is a function of x to the alpha, then it's slowly varying in the radial direction. Okay, so when a gradient hits the x to the alpha part, then, so for example, in the transport term, you should get a small constant in the front. Okay, you can play the same game in the angular variables. Okay, so if you do it correctly, you can essentially annihilate this transport term. So this is a pretty technical issue in how you actually establish what I'm saying, but that's the idea. So if you further introduce non-smoothness in the angular variable, and you impose axisymmetry, so that means you fix the z-axis and you say that the velocity is invariant under rotations fixing the z-axis. And you also impose that the velocity does not swirl around that axis. Then you can reduce the equation to this simple equation. So this is that Riccati type equation. And for this one, it's not difficult to establish finite time singularity. So actually, it is a Riccati equation, and if you integrate by parts in the right way, so if you apply this operator L12 to this equation, where it's defined by this, so this is that same type of operator, the R bar operator I discussed. And the fundamental question one has to study after you establish a singularity for this model is how do you go from this to the full equation? Okay, so so with yeah, I'll be done in 2 minutes. So sorry for taking too much time. So it turns out that if you work in the right class of solutions, you can think of it as a basically just a stability problem. Okay, so for this alpha equals 0 equation, there are exact solutions of this form. They're exact self-similar solutions. And then you can imagine that maybe you can use an implicit function theorem type argument to establish existence for this type of equation, for the full equation when alpha is positive, by sort of modifying some of the parameters. So you have to modify the scaling. So modifying the scaling was one very important thing we learned from a previous work with Inji Jiang. Okay, so this is a kind of a deeper discussion about the linearized operator and things like that has to be discussed. And okay, using some stability or coercivity for the linearized operator, you can establish the following theorem, part of which is in collaboration with Nader Masmoudi and Taj Ghul. So there exists a finite energy and C1 alpha solution for the 3D Euler equation, which develops a singularity in finite time. Okay, and yeah, so this particular construction we did cannot really be pushed to C infinity because of the rotational symmetries we put and some other things. But if you relax some of the restrictions we put, then okay, one can hope that you get closer to smooth solutions. And it seems like this is this might be possible. Okay, so I think I've gone over time, so that's good enough. Thank you.